This is Math 139, Section 2.1. We're going to talk in this section about power functions. Power functions are functions that have a very specific form. F of x equals x to the n power. The exponent, the n itself, is called the degree of that power function. And I'd like to investigate what the graphs of power functions look like for values of n that are positive integers, so 1, 2, 3, 4, 5, etc. X to the first, we'll actually leave that one off because we already know that's just a linear function. But let's explore things like x squared and x cubed and so on. I'm going to take a look at these in Desmos. So if I were to type in y equals x squared, we're familiar with that one. We know it's a parabola. Watch what happens if I change the exponent. There's x cubed, and there's x to the fourth, and x to the fifth, and the sixth, and the seventh. Are you noticing a pattern? All of the odd power functions have similar looking graphs. They all have this sort of a wave look to them. While all of the even-powered functions, to an even here, like x to the sixth, have this look that's somewhat similar to a parabola. The larger the exponent, you may have noticed, the flatter the vertex gets, but at least superficially, it's somewhat similar to a parabola. So I'm going to make a couple of conclusions here. I'm going to say that I get kind of a slightly flattened parabola when I graph y equals x to the n for n even. But I get this kind of a wave-like function when I graph y equals x to the n for n odd. We'll be using those as our prototypes or our parent functions to graph some transformations. I want to remind you about the transformations that we discovered for x squared, and then we'll write them in the form that we would want to write them for these new power functions. A multiplier of a for the power function x to the n would look like a times x to the n. And remember, that changed the width of our graph. It's basically a vertical stretch. It gets taller and narrower for a greater than 1. And for a less than 1, it gets wider. Oops, wider. What happens if we multiply our function by a negative 1? Specifically for our power function, that would be minus x to the n. You may remember again that that flipped it upside down, or we often say it reflected it across the x-axis, or the mathy way of saying it. If we replace the x with either an x plus h or an x minus h, those are horizontal shifts to the left or the right. If I were to write that in the power function form, it would look like x plus h to the n. That would be moving our graph left h units, or x minus h to the n, which would move our graph to the right h units. If I add or subtract a value to the function itself, not the x, but the whole function, that shifts things up and down. So the power function form of those would look like x to the n plus k, which would move our graph up k, and x to the n minus k, which would move our graph down k units. So the same transformations that applied to the x squared graph, the parabola, are going to apply to our power functions. And we'll apply those shifts to these shapes, these parent functions. Now again, I'm not going to worry about being super accurate with my exact points. What I'm really looking for here is a general shape. So our first example, we want minus x minus 3 to the 4th power. Our basic shape, our parent function, is going to be x to the 4th power, which is going to be one of those U-shaped functions. As far as transformations, we've gone to the right 3, and it's also reflected across the x-axis or upside down. So I'm going to move my usual vertex of the origin to the right 3, and then I'll show my U-shaped graph upside down. And that's as accurate as I'm asking you to be. If we want a really accurate picture, we'll use a graphing technology. But for our purposes, just a basic idea of where that graph is and what it looks like is all I'm after. The domain, you can plug any value in for x. This goes left and right forever, so minus infinity to infinity. But for the range, the largest y value would be 0. So we go from negative infinity to 0. Remember, we always go from smallest to largest. So I list the negative infinity first, and then we stop when we get to 0. All right, what about this one? Our basic shape is going to be like y equals x to the 3rd here, which is one of these wavy shaped graphs. This one's been shifted left 4 and down 2. So if I go left 4 and down 2, and then just graph that kind of a wavy looking function like that. That's going to be the basic shape of the graph. Its domain goes from negative infinity to infinity, and notice so does the range. It goes down forever, and it also goes up forever. All right, that's the end of section 2.1.